geometric word problems using quadratic equations. In this video, we'll solve three geometric word problems that require solving quadratic equations. We'll interpret results in terms of the problem and reject solutions that don't make physical sense. We'll also include units with our answers. A lawn currently occupies all of your square front yard, but you want something that needs less water. The landscaping plan you've decided on will decrease the length of the lawn by 6 feet and the width by 8 feet. The new area of the lawn is 224 square feet. What were the old dimensions? How much is the difference in area? The old lawn was square, and so all the sides were S. One side now is 6 feet less, so S minus 6, and the other side is 8 feet less, so it's S minus 8. The new area of the lawn is S minus 8 times S minus 6, length times width. But it's also equal to 224, tells us in the problem. So that's going to give me a quadratic equation. S squared minus 14s plus 48 equals 224. I'm trying to find the old dimensions, so when I solve this equation for S, that will tell me the old length of the sides. To solve it, I need to get 0 on one side, so I subtract 224 from both sides. I've written the factor pairs for negative 176, and I do have one that has a difference of 14, so my quadratic factors, 2s plus 8 times s minus 22 equals 0. That gives me two solutions. S is the side of a square lawn, and it can't be negative 8 feet. So the solution that works is 22. The old side of the lawn was 22 feet. And that's the answer to the first question. What were the old dimensions? The next question is how much is the difference in area? So the old lawn had an area of S squared, 484 square feet. So the difference in area is 484 minus 224, which is a difference of 260 square feet. Now each square foot of lawn requires 0.62 gallons of water twice a week. But your new landscaping doesn't need water, so how much water are you going to save? Well, you're going to save the water that you would have spent on this 260 square foot area that's now re-landscaped. So we're going to multiply 260 square feet times 0.62 gallons per square foot, and we're going to do that twice a week to find out how much water we use in a week. I get 322.4 when I multiply it out. That's gallons per week that we save. So by setting up this equation with the new area, we've been able to find the old dimensions, the difference in area, and the amount of water that we're saving every week. On the way to school, it's early morning, and you can cut diagonally through a parking lot. On the way home, the lot is busy, and so you have to walk around the edge. The length of the lot is 5 meters less than twice the width, and the area of the lot is 1,125 square meters. What are the dimensions of the lot, and how many meters less do you walk on the way to school than on the way home? Well, let's call one side of the parking lot length and the other width, and the length is twice the width minus 5. That's what 5 meters less than twice the width means. And then the width is the other side here, and the area is 1,125 square meters. So since we want the area of a rectangle, we're going to multiply 2w minus 5 times w. 2w squared minus 5w equals 1,125. And if I get 0 on one side, I have a quadratic equation. Now probably this is factorable, but finding the factors of 1,125 sounds extremely tedious. So instead I'm going to use the quadratic formula to solve. That way I can use my calculator to simplify it. The square root of 9,025 is 95. And so my two solutions are 5 plus 95 over 4 and 5 minus 95 over 4. Now remember, I'm looking for a side of a rectangle, and 5 minus 95 is going to be a negative number, so I'm just not even going to bother to evaluate that answer. 5 plus 95 is 100, and divided by 4, that's 25, so I like that answer. That gives us that w is equal to 25, because my equation was in w. If w is 25, the length must be 2 times 25 minus 5, or 50 minus 5, which is 45. Now I'm measuring everything in meters. So now I have that the width is 25 meters and the length is 45 meters. And you can check and multiply those together to see that you get 1,125 square meters. So I answered the question about the dimensions, but what about how many meters less do you walk on the way to school than the way home? Well, I have a triangle, and it's a right triangle, so I can use the Pythagorean theorem to find the length of the hypotenuse. 25 squared plus 45 squared equals c squared. So c squared is 2,650. If I take the square root, it's not a perfect square, but it's approximately 51.5 meters. If you walk 70 meters on the way home and 51.5 meters on the way to school, that's 18.5 meters difference. So you walk 18.5 meters less on the way to school than on the way home. You have 24 feet of deer fencing to enclose a rectangular garden behind your house. The fence will enclose 3 sides, and the house will provide the 4th side. What's the largest area you can enclose, and what dimensions will the largest area have? When I'm looking for a largest, or a maximum, or a smallest or a minimum, I need to write the thing I'm finding, in this case area, as a function. Now I'm enclosing a rectangle, so that I know the area equation is area equals length times width. And the constraint on this is that there's only 24 feet of fencing. So that 24 feet has to cover a length, a width, and another length. So 24 has to equal 2 lengths plus 1 width. Now to get the area in terms of only one variable, I'll subtract 2L from each side of this equation, and I'll get 24 minus 2L equals W. And I can replace W in the area equation with 24 minus 2L. So now I have that the area is equal to the length times the width, but the width is 24 minus twice the length. And so now area is written as a function of length. If I multiply it out, I get 24L minus 2L squared, and that's a parabola. The coefficient of the squared term is negative, so it's a parabola that faces down. The factors are L and 24 minus 2L, so the zeros are at L equals 0 and 24 minus 2L equals 0. 24 minus 2L equals 0 gives me a value of L equal 12. Now let's see what those mean physically. The area is 0 when there's no length. When the length is 0, the 24 feet of fencing just run along the side of the house and enclose no area. So that's when L equals 0. Now if L equals 12, all the fencing is used in the length. So that's what the zeros mean for this function. If I graph it, the input is a length measured in feet, and the output is an area measured in square feet. The greatest area occurs at the vertex. Now the zeros are 0 and 12. That's when the area is 0. So the vertex has to come halfway in between those two. It comes at L equals 6. If I evaluate the area function when L equals 6, I find the maximum area. So 24 times 6 minus 2 times 6 squared is going to give me 144 minus 72, which is equal to 72. So the area of 72 square feet is the most area I can get out of those 24 feet of fencing. I already know the length dimension. The length is 6 feet. Now W is 24 minus twice the length, so if I stick 6 in for L in that equation, W equals 24 minus 12, 12. Even though there's no physical parabola in the problem, you just have a rectangle, the area function, given the relationship between the two sides, is a parabola, and so we can find the maximum at the vertex.